Good morning, gentlemen. Thank you for the opportunity. Before I start my presentation, let me introduce myself. I'm Utomo. I'm from Badak LNG, an LNG company in Indonesia. And my background is electrical engineering. I have been working in Badak LNG since 2015, and then I got an assignment as electrical engineer from 2015 until 2019, and now currently I'm at strategic and business corporate strategic and business in Badak LNG as a strategic planning specialist. Okay, in this good chance, I would like to present my research about the atmospheric electricity evaluation advanced stack of knockout drum in Badak LNG Indonesia. We have 5 agenda here, and the first is our company profile, and then the second is background and objective. The third is basic theory. The fourth is atmospheric electricity evaluation, and the last is conclusion and recommendation. This is Badak LNG Indonesia, which is located in Indonesia, specifically in Borneo Island, or we can call it, this location is near the Brunei Darussalam and Malaysia. And then this is the position of our company compared to another LNG in worldwide. And then our company profile, we have LNG production capacity up to 22 MTPA, and then the LPG is up to 1.2 MTPA, and then the condensate production capacity is up to 1 million barrel per year, and we are producing LNG since 1977, and then currently we have safe work days hour up to 5,000 days, and then we have safe work hours up to 100 million hours. Then we go to the next agenda. It's a background and the objective. Currently, actually it was happened in our plan, on 10 October 2016. A fire occurred at the fan stack of knockout drum. The knockout drum is the entrance of gas inlet, which will be processed into LNG product. And then, as we know, the fire, based on fire triangle, the fire of the fan stack of knockout drum could be caused by 3 elements, the presence of 3 elements. The first is oxygen, the second is flammable gas from the feed gas, and then the last is ignition source. And then from the investigation, there are 2 causes from the ignition source. The first is corona discharge, and the second is a lightning strike. And we called these 2 items as atmospheric electricity. And then currently this is the layout of knockout drum area. This knockout and the altitude of knockout drum area is fairly low. It was assumed that the fan stack of knockout drum will not suffer the atmospheric electricity, and then there are some high trees that surrounding the knockout drum area, so it is assumed that the knockout drum area is safe from atmospheric electricity, either from corona discharge or lightning discharge. However, from the investigation, the fire incident is caused by the presence of 2 causes. So in here, my research is to evaluate the corona discharge on the fan stack of knockout drum, Second is to evaluate lightning strike on the fan stack of knockout drum, and the last is to design a protection that can protect the fan stack from the atmospheric electricity. Next, we move to the second agenda, is basic theory. Okay, in here we know that this is the Iso Keraunic map, which the Badak LNG is located in a yellow region in here. It means that PT Badak LNG will have a thunderstorm day up to 180 days per year, or almost half a year. So it increased the potential of occurrence of the atmospheric electricity. And then if we look at this thunderstorm, as we know, during the thunderstorm, the lowest layer of cloud has a negative charge. It induces the ground to have a positive charge. And then, because there is a different charge between cloud and the ground, there will be electric field from positive to the negative. The electric field will follow this formula. If the value of the electric field is more than 30 kilovolt per centimeter on the dielectric strength of air, a fan stack will have high probability to be struck by lightning because it has smaller distance than another. And also, we know that the electric strength is the ability of air to prevent electric current flowing from negative to positive. And then for the second is if during the thunderstorm, it also affects the electron and proton in the air. And then the proton will move up to the cloud and the electron will go down to the ground. There will be equipotential VA, which is made up from the electron that goes down to ground. Because there is different charge between equipotential VA and ground, there will be electric field from positive to negative. The electric field follows this formula. If it is greater than the 30 kilovolt per centimeter or the dielectric strength of air, a fan stack will have high probability to have corona discharge because it has more distance than the other. That is the basic theory. And then we move to the atmospheric electricity evaluation. This is the next agenda. And in here I use two methods to evaluate the atmospheric electricity. The first is electric field simulation. I use computerized simulation to prove the corona discharge. And then the second, I use the rolling sphere method based on the standard of NFPA 780 and IC 62305-3, and also I use my company general specification. This method will be used to prove the lightning strike. And then this is the electric field simulation. The simulation is used to show the electric field distribution, or E, between cloud and vertical fan stack. The cloud is modeled as a solid cylinder, and then the fan stack is modeled as hollow cylinder. The voltage is applied between them, and then there will be a distance between them. And this is the model and parameter simulation. In here we model the cloud with 400 meter S diameter. There are 5 5 meter as the thickness, and then we use the distance between the cloud and the fan stack is about 4 kilometers, and then the fan stack will have a height at 3 meters and the diameter is 16.8 centimeter, and then the potential between the cloud and the fan stack is about 500 kilovolt, and then this model will be simulated using the electric field simulation. This is the simulation in the software. I use the Asensoft Maxwell software. And then this is the simulation result for the existing condition. We can see that most of areas at the top of the fan stack have electric field up to 35.2 kilovolt per centimeter. It means that it is larger than the dielectric strength. So we can say that the coronary discharge are present on the top of the fan stack. And this coronary discharge will could ignite a fire when flammable gas is released out from the fan stack. So this fan stack need protection. And then the second method, I use rolling sphere method to prove the presence of a lightning streak. In here, this method to identify the areas of structure that need protection from lightning strike, and an imaginary sphere is rolled over the structure, and then the radius of imaginary sphere follow this formula, which is the radius is 10 times the lightning current power of 0.65 and the lightning current in kiloampere. And for Badak LNG, based on the research, the lightning current will be about 40 kiloampere. So the radius will be about 109 meters. And this is the illustration of rolling sphere. In here, we roll the sphere with diameter 109 meters through the ground object, and then every ground object which is touched by the sphere will be struck by lightning protection in here, or we can say that the red line in here require protection because it will be struck from the lightning streak. And then this is the rolling sphere method on the fan stack of knockout drum. We can see that because the rolling sphere radius is up to 100 meter, so the area is look small. Yeah. And then this is the evaluation. We can see here that the rolling sphere method, the rolling sphere touch the fan stack, so the lightning will strike the fan stack of knockout drum. If flammable gas is released out from the fan stack, the lightning strike could ignite a fire, and so in here lightning protection is required. And then from two evaluation, we can have in here summary that the electric field simulation shown that coronary discharge will present at the top of the fan stack, and the rolling sphere method shown the lightning will strike the fan stack of knockout drum. So in here the fan stack requires protection. The protection system shall be able to elevate the coronary discharge at lightning striking point to higher position, and we design the atmospheric electric system protection system from the NFPA, IC, and my general specification, and then we evaluate the protection using the rolling sphere method and also the electric field simulation. And we have a target that the fan stack will be safe from the atmospheric electricity. And this is the design. The protection will consist of 3 items: air terminal, system, ground conductor, grounding and grounding system. And then this is the model of our protection for the atmospheric electricity. In here, we have a distance between the possible maximum gas released out from the fan stack and the top of the protection system is about 1 meter. And then the distance between the fan stack and the lightning protection is 0.6 meter. And then we also use the grounding rod, which flow the current from the lightning strike in here to the ground. And then this is the evaluation. We start with the electric field evaluation. This is the design for the atmospheric electricity protection system. And then in here we evaluate that we can see that the corona discharge evaluation show most of areas is have electric field about 40 kilovolt per centimeter, with the top of the fan stack is about 27 kilovolt per centimeter, or it is smaller than the electric strength of air. It means that the fan stack is safe from the corona discharge, but from the top of the air terminal, we can see that the air terminal will have 100 kilovolt per centimeter. So it means that the corona discharge will save in the fan stack and it moves to the top of the air terminal. So the fan stack of Kinokot drum is safe. And for the lightning strike, we use the rolling sphere method. In here, we roll the sphere, and we had that the atmospheric electricity protection system elevates the lightning strike point from the fan stack to the lightning terminal or air terminal. So the lightning will strike the terminal, not the fan stack. So in here, the fan stack of knockout drum is safe from lightning strike. We can see from these two evaluation for the atmospheric protection system, we say that the protection system can save the knockout drum from the corona discharge, and then the second, from the rolling sphere method, we can have the lightning will not strike the fan stack of knockout drum. So in here, the fan stack of knockout drum is protected from atmospheric electricity, both from the corona discharge or the lightning strike. And we have the last agenda in here, conclusion and recommendation. The first conclusion is corona discharge occurred at the top of the fan stack of knockout drum. We prove it with the electric field simulation. And the second, the lightning struck the fan stack of knockout drum when we prove it with rolling sphere method. And the last, we have atmospheric electricity protection system that can protect the fan stack from the atmospheric electricity, both corona discharge and lightning. And the recommendation from this research is you have to install the atmospheric electricity protection system in every fan stack of knockout drum to save the knockout drum from the atmospheric electricity system, both corona discharge and lightning discharge. Thank you, gentlemen, for your attention. If you have any question, do not hesitate to contact me and ask me. Thank you. Good morning.